So I'm going to talk about SAI for tunnel security. This is basically IPsec applied to IP tunnels. And we support it in hardware, so the SAI is there for programming the hardware. And that allows us to do it at line rate. And since this is SAI, of course, this is a case where the tunnel is terminated in a switch, which is often the case when we get to the application cases in a couple of minutes. So I'm Dipankar Acharya. I work in Arista Networks. I worked on defining this and getting it implemented from our silicon partners, and also with the software engineers inside the Arista internal implementation, and defined the SAI APIs for the feature. So why do we need tunnel security? The typical case where it comes up is when you have a tunnel going across an untrusted network between two sites. And there are variations of that. The two sites could be two data centers. It could be between an edge site and a data center. So in the first case, it could be two data centers in completely different geographies. Take example of, say, San Jose and New York. And the edge site and a data center could be potentially San Francisco edge site is homing into a data center in San Jose. As you can see, all my world is revolving around San Jose. And there's also the case where the customer sites could be connecting to an edge site or to a data center directly. It also can protect the data and isolate the data between different tenants in a multi-tenant situation when it is going across different sites. So what makes the tunnel security possible today, and why now? We had used ad hoc methods before, like Macsec over a tunnel and things like that. But the IPsec and IPsec v2 have been standards for a long time and have been implemented in software. The line rate encryption capability that came from Macsec is now available in many switches. There is no reason that the switch cannot handle a different packet format and use the same technology for doing IPsec encryption. So that was a logical step, what made it possible. And then we essentially had to make sure that that gets implemented in the pieces of silicon that we use in the underlying cases. Now, I've talked of only hardware implementation. There are use cases where one end of it is a server, where the throughput requirement is not that high. And so it could be a server on one side, possibly accelerated with some crypto accelerator. And it's a software implementation that is talking to the switch on the other side. So what does IPsec bring to a tunnel? So basically, how does it work? So the packet is protected using encryption for secrecy and using a hashed value key to the secret key for checking integrity and authenticity. Also, it is got a sequence number which can be used to check anti-replay. Basically, it's anti-replay protection. Now, all of that requires a little bit of extra information to be carried outside of the encrypted packet. So there's a ESP header that carries a SPI field that identifies the security parameters to the decryptor, the receiving end. And there is a sequence number in there also that was for the anti-replay. So an IPsec packet essentially needs a transport header, IP transport header outside, followed by the ESP packet, and followed by the encrypted payload. And we'll go into more of that later. Now, this is all at the endpoints. The transit nodes, there is no change. It's standard IP routing in the transit nodes. So we introduced 3 packet formats for this. The first one is a straight-up IPsec tunnel, as defined in RFC 4303. And essentially, it is taking an IP packet along with its header and payload, encrypts the whole thing, and then imposes outside a ESP header and a tunnel IP header for transport. Now, if you notice, the inner packet with its header is encrypted, which basically means many flows can share a tunnel. Now, if we didn't encrypt it, very often through the network, through the transport network, the inner packet's entropy is used for multipathing. But once you encrypt it, it's not available. So this packet has to traverse from the encryption point to the decryption point using one path only. And that becomes a little bit of a challenge when we're dealing with very high speeds, because we currently already have hardware that supports it at 400 gig, and 800 gig is coming soon. So then we use the second packet format where we add an extra UDP header in the clear outside of the ESP header. So right after the tunnel header comes the UDP header. So now we can use the source port of the UDP header for entropy, which is often used for VXLAN and other things. And you can do multipathing. However, at these speeds, if you're running full speeds across untrusted networks, which can have different paths and different congestions, the anti-replay can become very challenging because the amount of packets that get reordered can get very hard. And at these speeds, the cost of maintaining a large window for reordering, for anti-replay detection is pretty expensive. So our normal recommendation here is potentially, and do something else. We'll come to that later in the next slide. So now the third format that we have is VXLAN in security. So VXLAN already has an IP header that is identifying the tunnel endpoint. So it makes no sense to put it in another IP tunnel for transport. So in this case, we use the IPsec transport mode. So encrypting the payload starting from the VXLAN header, so right after the tunnel headers. And then because of the encryption, we have to introduce the ESP header. And for multipathing, we introduce the UDP header in the clear, which is an extra header. Okay. So what is the underlying switch architecture that supports this? So normally in the switches, there is a packet processor that takes care of the forwarding of every packet. It also is capable of tunnel termination and origination. So we use that capability for originating and terminating the IPsec tunnels also. And then there's a separate security engine. Now, I'm talking functional blocks here, not yet necessarily chips and components, but there's a security engine element that is doing the encryption and decryption, the crypto transformation on the packet. So this maps very well in situations where actually the security engine is outside of the switch ASIC, and that has been often used in the Macsec context where it is attached to ports. It's also useful because one single security engine can typically handle a single very high-speed port or a handful of lower-speed ports. So a switch will be associated with multiple security engines. So even when it is integrated in the same chip, which we have now, since there are multiple security engines, maintaining a certain decoupling between them helps. And so the programming model, we introduced this idea that the SAI index, which is Security Association Index, identifies the database that the security engine is going to use for the packet processing. And the tunnel originator is going to provide the security SAI index so that it is tied to the tunnel, right? So we have both implementations now available in hardware. Right from the beginning, we worked with silicon partners. Credo had a Macsec chip, which also does IPsec. And Broadcom has multiple switches which integrate the security engine inside. Okay. And I think more recently, Broadcom has a PHY chip that also integrates IPsec. So the SAI constructs for this, the security association is the key one for encryption, so we have an object for that. And And then we need actually each of the security associations are unidirectional. So for each tunnel, we need 2 security associations on a switch. Plus, we added a couple of extra objects. They were actually to add attributes at the switch level and at port level. And we exposed this SAI index that is used by hardware to SAI to bind the tunnel to the security association. Going into a little more detail of what we added there. So we added 3 new tunnel types for supporting the 3 new packet formats. We added 3 object types, SAI IPsec for the switch level IPsec attributes, SAI IPsec ports that is attached to each port for the switch level IPsec attributes for the port, and SAI IPsec SA for the all-important security association that is really bringing the encryption capability here. So what are the sequence of things that need to happen to enable an IPsec between 2 switches? So first, the 2 endpoints have to trust each other, so they need to be authenticated in some fashion. Just as you establish for any tunnels, you can use pre-shared keys between them or a PKI infrastructure. After that, the NOS uses IKE v2 protocol between the peers. And this establishes a connection between them and it does a Diffie-Hellman exchange, so now they can secretly share information. And in phase 2 of IKE, it exchanges security policy and security keys, the security association materials, the key materials. After this phase 2 exchange is over, the NOS can actually is capable of populating the hardware and prepare for IPsec transfer, right? So the NOS uses SAI to make this configuration. It sets up a SAI tunnel of one of the 3 IPsec types. In this example, I'm saying IP and IP ESP, which is the IPsec tunnel. It configures at least 2 security associations, one for the egress, one for the ingress. And for the egress security association, it attaches that to the tunnel so that the tunnel can dictate what encryption is done for an outgoing packet. So now we can go over the data flow for a packet as it traverses the switch once programmed configured in this fashion, right? So when a clear text packet is forwarded to a tunnel interface, the SAI basically allows it to, the SAI programming of the switch allows it to impose the tunnel header and find the associated security index from the tunnel attributes, the SA index. Now the packet is routed now with the tunnel header to a transmit port ID, which identifies where it will exit the switch. Now, each transmit port ID is associated with a security engine. And so this directly maps to a security engine to send the packet to. So the hardware sends the packet to that security engine for further processing. The security engine uses the SA index to identify the security association that is programmed there with the SAI attributes, and then transforms the packet for encryption, prepares a full packet to go out, which is now a secure packet. And it uses the transmit port ID to send it out to the correct output port. So in this diagram, just the packet processor is on the left, so the data flow is from the left to right, and the last thing it exits is the security engine and the port, right? In the next diagram for the receive packet flow, the packet arrives on the left-hand side is the security engine now, and which processes the packet first and then goes through the packet processor. So the security engine essentially looks at the ESP header of the packet, identifies the SPI, security parameter index, which helps it find the right security association programmed into it, which gives it the keys to decrypt and validate the packet. Okay. So the verified packet now, after the decryption, is a clear text packet along with the validation status is sent to the packet processor. The packet processor checks the verification status, and if in case of failure, applies the appropriate policy to drop or trap it. Otherwise, it removes the tunnel header and processes it just like any other tunnel, uses the inner packet header, which is now in clear text and decrypted to forward the packet. So what's the calls to action? Well, it's a little straightforward. We need to get it going and use the API in the NOS and have the drivers ready for SAI. The API is ready, the hardware is ready. With our proprietary switches and software in Arista, we're already shipping tunnel security. We need to get the SAI drivers ready and the NOSes like Sonic and WebPOS ready to make use of it. We need to revive the SAI IPsec subgroup to make that happen. And that's fundamentally it. That concludes the presentation. So I guess we have a couple of minutes for questions.